everybody. I have a couple of announcements to make. Next Thursday, we will not have a colloquium on account that it's a holiday and campus will be closed. So that's next Thursday. The other announcement is for CS majors. Please attend the lecture and note the information in here. This is about 2 o'clock, maybe with a few minutes, 2 and 5 minutes or so. I'm not sure about Darwin 24, it may be 24, maybe 28. Anyway, once you are in the basement of Darwin, you'll find a place where the lecture will take place. So today we will hear from Dr. Rebecca Hartman-Baker, and she will talk about paradigms and parallel computing. Let's welcome the speaker.
Right, thanks everyone. So yes, my name is Rebecca Hartman-Baker. I'm the User Engagement Group Leader at NERSC, which is Supercomputing Center. So first I'm going to tell you a little bit about myself, and then we're going to move on to the actual purpose of this talk. So I work at the National Energy Research Scientific Computing Center, which is called NERSC for short, and it's a big supercomputing center at Lawrence Berkeley Lab. Before that, I worked at the Pawsey Supercomputing Center in Australia, and I worked at Oak Ridge National Laboratory. My area of expertise is scalable numerical algorithms, so algorithms for solving hard problems on supercomputers. I have a PhD in computer science from the University of Illinois at Urbana-Champaign. I got my bachelor's in physics from the University of Kentucky, and I'm the proud mother of 2 kids. I have my son Vincent, who's 9, and my daughter Elena, who's going to turn 1 in just a few more days. Okay, so first we're going to have a little glossary here. Has everybody heard of a flop? Anybody heard of a flop? It's when I tell a joke and nobody laughs. Right, okay, but it also means a floating point operation. So it's just any basic arithmetic operation involving a decimal point. So 1.1 plus 1.1 equals 2.2 is a flop. Okay, we measure flops, floating point operations per second. That's sort of how we talk about the power of a computer, like a supercomputer in particular. Now, people may have forgotten their metric prefixes, so we're just going to sort of touch on these for a second here. So if we have the prefix here and we have the powers of 10. So 10 to the negative 1 is deci, right? Like decimal. Kilo is 10 to the 3rd. Mega, 10 to the 6th. Giga, 10 to the 9th. Tera, 10 to the 12th. Peta, 10 to the 15th. Exa, 10 to the 18th. Okay? Everybody has that, right? There's going to be a quiz at the end. You're all going to have to reproduce this. No, you're not. Okay. So, what I'm going to talk about is history. Okay? I am now a manager. They took out part of my brain, so I don't get to do any technical work very much anymore. But I really love history, so I'm really interested in the history of computing. So we're going to talk about different eras of time, which I classify in the following ways. So we've got the sub-flops era, right? We're not even talking 1 flop, not even 1/10 of a flop. Okay? People were computing even back in the the historic times, maybe not the prehistoric time. Okay? Then there's the deciflops era, and that was from about 1640 to 1850. So people could do about 1/10 of a flop per second. Okay, then we've got the flops era, 1850 to 1940. We've got the digital era, 1940 to 1980. The parallel era, 1980 to 2007. The petascale era, 2008 to the present. Okay, now everybody remembers, right, what peta stands for, right? 10 to the 15th. Okay. So, we're going to start with the subflops era. Okay, Bronze Age computing. I bet you never thought you would hear those 2 terms combined. Okay, so in the Bronze Age, people did do computations, but it was really hard to compute anything because they hadn't really invented like the decimal number system or the concept of 0 yet or anything like that. So any computations that they did do, they would make sure to store it in a table. and then they could reuse it that way. So they had a lot of applications in commerce and science. And this is a picture of the world's oldest known mathematical table from 2600 BCE. Okay, so what did they do with their computations, right? Well, a big thing was the area of fields, because that was an important thing in commerce back then. They do accounting, they do unit conversions from one type of unit to another. They actually computed arithmetical, like reciprocals and coefficients and things like that. They did Pythagorean triples, and they even did squares and square roots. And you can see the squares would be important in the area of fields. Okay, they would also do computations for astrological predictions to figure out where the sun and the moon and the stars were going to be, and that sort of thing. They also had these things called I'm never going to say this right, ephemerides, for predicting astronomical occurrences. Okay, and while this was going on in ancient Sumer, Babylonia, and Assyria, there were other cultures where they were also computing stuff. It's not strictly a Western thing. So the Pachanga tables in India they date from the 2nd millennium BCE, and Chinese, they also were computing tables as well. Okay, the Iron Age computing, right? The Iron Age is really like the classical era. It was what we would call it in Western civilization. So there was a famous person named Hipparchus, and he developed these models of motion for the sun and the moon and the solar eclipses, and he also developed some trigonometric tables. Okay, I think we've probably heard of Ptolemy. Ptolemy, he had two main works, which was the Almagest and the Handy Tables. And in my secret notes, it says what those are, but I don't remember what they are. Sorry. Okay, then there was a mathematician who you've heard of, whose name you use all the time, but you just don't know it. And this is Muhammad ibn Musa al-Khwarizmi. Al-Khwarizmi, algorithm. He invented the algorithm. So he developed some astronomical tables. He introduced the decimal system to the Western world, the positional numbers. He did the first systematic solution of linear and algebra and quadratic equations, and he was pretty much the inventor of algebra. Okay, so in the medieval and Renaissance eras in Europe, they did these prostapheresis things where they would approximate multiplication and division using trigonometric formulas. But a big breakthrough was when they developed the logarithm, developed by John Napier in 1614. The reality is logarithm already existed. It was developed in the AD 200s in India. But the Europeans finally figured it out about 1,500 years later. So he was able to compute results that allowed him to find L in this following equation for n between 5 and 10 million. Okay? So, in other words, you can compute n from finding that out. Henry Briggs compiled a table of logarithms in 1617 with 8 digits of precision. There's a precursor called Gunter's rule, and then the slide rule. And those were developed. Does anybody, like maybe your parent or your grandparent, had a slide rule? No? Yes? Have you sort of seen those before? Okay. So the development of the logarithm was really crucial in the advances in science and like in astronomy and surveying and all these things. Once they had the logarithm, then multiplication and even division became a lot easier. Okay, so you might be saying, okay, that's really interesting, but like, how did they do that? Well, nobody really knows exactly how they computed the first tables. It was probably a collaborative activity, and they often would copy them to memorize it. The Babylonians developed an abacus in about 2400 BCE. The Chinese also developed the abacus, and even the ancient Mayans were in on abacus development. So they had an abacus that I'm not going to pronounce. And then we know that the ephemerides were produced collaboratively. They were constructed from the best available existing tables by teams of computers. So back then, up until about 1950, 1750, computer was actually a job title rather than a machine. And often these were international collaborations where people would correspond by mail and develop these tables. Okay, so they were also, in addition to developing the math and the stuff like that that you're going to need for computers, they were also developing the technology. So they developed a mechanical clock in 724 AD. There was the Banu Musa brothers, who were from the Arab countries, and they developed a hydro-powered organ and a programmable automatic flute player. That's pretty neat. And then there were also some actual computing devices. So the astrolabe and that was developed. There were a few other things. There was a torquetum that transformed between spherical coordinate systems. There was the castle clock, which was an astronomical clock. And some consider it the earliest programmable analog computer. There's a lot of invention in these days by all of the Arab mathematicians and technologists. Okay, and the final one on my list here is the plate of conjunctions that predicted the time of planetary conjunctions. It was able to perform linear interpolations. So I mean, that's pretty impressive if you think about how early on all of this was going on, 1,000 years ago or more. Okay, so we're going to enter into the decaflops era. Everybody remembers deca, right, as 1/10. So I think you could compute it would take about 10 seconds, probably, to compute one arithmetic operation in this era. Okay, so these tables, people really got into these tables. So they started really developing these tables in the early 1700s. And the Nautical Almanac, and the way they did the Nautical Almanac was they would have these freelance computers. So again, computer is a job title. So these people, and they would do it via regular mail correspondence through the postal service. They developed some more advanced computing machines. So this is actually a picture of the Shikard calculator, which was a precursor to the machine arithmétique, which was invented by Blaise Pascal. And it had a carry mechanism, so that when you added two numbers and they added up to 10 or more, it would carry the 1 to the next decimal place. There was also a non-decimal adding machine for use with English money, and that was developed in 1668. Okay, so a portable calculator with all 4 math operations was developed by Hahn in 1774, where portable still means it's really huge, right? It's not portable like stick it in your pocket. Another big development may not be clear to you all now, but the automatic loom controlled by punch cards. So there was this guy named Joseph-Marie Jacquard, and he developed the loom controlled by punch cards. And in fact, this picture right here is a picture of like a blanket that was produced using 23,000 punch cards. Okay, it's pretty impressive. So you all may not know why punch cards are useful in the computing, but we'll get there. Okay, so then finally another big one was the arithmometer. And this was the first mass-produced mechanical calculator. It was based on Pascal's and Leibniz's work, and started actually mass-producing it in 1851, and it actually went up through the early 1900s that they were mass-producing these. Okay, so you remember, everybody's all obsessed with tables, right? Because computations are expensive, so we need to preserve that information once we do it, right? So in 1793, the French Bureau du Cadastre, so that's like the Land Bureau, they were charged with producing logarithmic and trigonometric tables to 14 and 29 decimal places from scratch. Okay, and the project was headed by a guy named Gaspard Riche de Prony, and he was inspired by Adam Smith, who wrote about capitalism, to divide the labor up, sort of like Smith describes like in a pin factory. So they had a small advisory group of eminent analysts, so advanced mathematicians. They had 6 to 8 professional mathematicians, and then they had 60 to 90 computers who were relatively unskilled workers performing basic arithmetic. Okay? And in fact, in this era, this was right after the French Revolution, 1793. So this was actually the Guild of Unemployed Hairdressers. So the French Revolution had kind of destroyed the need for hairdressing, I guess. Most of the heads that used to get their hair dressed were no longer attached to the bodies. So the hairdresser guild, they were sort of out of work. But apparently they could do basic arithmetic pretty good. So they were the computers here. Now, this organization actually was the new standard for large table making projects through the 1940s. Okay? So this happened at the end of the 1700s through the 1940s. This is how all large computational projects were done before we actually had actual, machine computers. We had people computers. Okay, so then Charles Babbage, he looks really delighted in this picture, but he originated the concept of the programmable computer. His motivation was these table projects. So the unemployed French hairdresser guild, they were pretty good at accurately producing these numbers. So I think they had like 3 people who would do the same computation, and if they all got it right, or if they all got it the same, they would kind of figure it was right. The problem came when they were translating those computations into typesetting. So actually, the output of the Bureau du Cadastre was the big book of tables, and it had 7 errata. Okay, so everybody knows what an errata is, right? It's where you find a mistake in your book and you put out like a page that says, oh, here's on page 37, this should really be, some other number or whatever. So in that book, they had an errata, then they had an errata to that errata, then another errata to that errata, etc., 7 times. So Babbage was like, what if we could just do all of this with a machine? We could make the machine do these calculations and typeset it at the end, and there would be no mistakes. So he invented this difference engine. And the purpose of it was to compute the values of polynomial functions using finite differences. And in the end, this would produce these logarithmic tables or whatever, and they would go, and then it would make a typesetting of the results, and that would be, success, right? No more 7 times erratas in these books. Unfortunately, for a variety of reasons, his machine was actually never completed until 1991. But in 1991, somebody made a reproduction of it using the same technologies, I guess, that he used. So the same tolerances. So it wasn't as finely machined as one could do in the modern day. And they proved that it worked. In fact, I was at the Computer History Museum earlier this year, and they had one of these copies of this difference engine. It worked great. It was amazing. So people have also probably heard of Ada Lovelace. She was an acquaintance of Babbage's, good friend, actually. And she built upon Babbage's second computer design, which was the analytical engine. Now, the analytical engine really was never completed. He had sort of made a mini difference engine, but he never made a full analytical engine. But the idea was that it would be programmable with punch cards like Jacquard, right? And she actually was the first person to think about what else you could do with it besides just compute these tables. So she developed a program to compute the sequence of Bernoulli numbers. And in fact, somebody went later and checked her program, in the modern day. And there was sort of like one little minor mistake, but other than that, it was a perfect algorithm for describing exactly how you would compute these numbers. So, speaking of numerical methods, this was really the golden age of numerical mathematicians. So we had a lot of great mathematicians in this era, the deciflops era. Gauss, everybody's heard of Gauss, right? Like Gaussian elimination, Gaussian curves. Fourier, like Fourier transforms. Jacobi, bunch of them. They were all out there. This was really a great era to focus on these scientific and engineering applications. They were able to make these big advances in science and engineering, and these mathematicians were part of that. But they couldn't have known that their work would actually be instrumental more than a century later in digital computing, right? Because they couldn't even conceive of a digital computer. So I can't really talk about all of the numerical methods unless you all want to just stay here for, forever. But I'm just going to talk about a few that I think are kind of interesting. So one of my favorites is iterative methods. So a lot of times you want to compute the solution of like a matrix times a vector. You want to compute what is the vector ax equals b, right? You want to compute x. You can use an iterative method. So an iterative method is just a mathematical procedure that generates a sequence of improving approximations to the solution of a problem. So one example of this is stationary iterative method for a system of linear equations, sometimes called a relaxation method. Has anybody heard of those? I don't mean relaxation methods like massage. I just mean like, mathematical relaxation. Okay, not very many people. Okay, so an iterative method solves a system with an operator that approximates the original operator. And stationary, what that means is that the operator just stays the same. So in this case, you just do a matrix vector multiply over and over and over again, and then you're going to get the solution eventually. So this is what a relaxation method does. So you solve a linear system of equations with the form, this is our next iterate, this is our previous iterate. We have g, which is our operator, plus some constant. So you choose g and c so that it's a fixed point of this, so that x is equal to gx plus c. Okay, so when you reach the true solution, you're there. And so you choose g by splitting up a. Usually you say a equals m minus n. And then you take g, you set it to the inverse of m times n, and c equals the inverse of m times b. And it's going to converge under certain circumstances. So we'll say that always happens. So the question is, so how do you pick m and n? Right, so if you take your matrix A and you divide it up into parts, so you've got L, which is your lower triangle, you've got D, which is the diagonal of the matrix, you've got U, which is your upper triangle, then you can do the following. You can do the Jacobi method. So you set, basically you take out the diagonal and you use that as the sort of inverse one that you're going to invert, and then it'll work. It's pretty slow. It requires twice as much storage as maybe some other methods, but it works really well. There's also the Gauss-Seidel method. Okay, and it actually is more efficient. It was developed by Gauss and Seidel, and the Jacobi method was developed by Jacobi, obviously. Otherwise, it would be named something else. Okay. So we're moving along into the flops era. Okay, so we can do about one floating point operation per second. So mechanical calculators, these were a big deal. So these were developed first starting in about the 1850s. So the Schweitz family, they developed a full-scale difference engine. It wasn't as good as what Babbage had designed, but at least it existed, unlike what Babbage had designed. The next thing was the comptometer, and that was developed by Dorfelt of Chicago in 1884. Also invented a printing desk calculator a few years later. And this was the first time where you actually enter your operands by punching buttons rather than dialing them in. So that was a pretty big deal. Those were highly successful. Herman Hollerith. Has anybody heard of Herman Hollerith? Yes, some people have. Okay, so Herman Hollerith was a Census Bureau employee. And in 1890, they were kind of worried because the 1880 census had taken 7 years to complete all the tabulation of it. And they calculated that the 1890 census was going to take 13 years. So in other words, it was going to take longer than before you even got to the next census. But he was able to figure out a way to process the data in 4 years and far under budget using punch cards. He went on to found the Tabulating Machine Company, which later became IBM. So he was really the father of IBM. So his tabulator was for a specific purpose in 1890, and so it wasn't really very profitable for him, but he did develop more general purpose tabulators later where you could use a plug board to adapt it to different applications. And then they standardized the punch card with 80 columns and rectangular holes. And they had a multiplying punch, which was just a machine where you would put in a punched card and it would output the punch that would be the product of the two numbers on your punch card. Okay, so in the Great Depression, people needed jobs, right? So they once again started doing these big math table projects. So the WPA had a math table project. They had 450 people that they employed to do these. Most of them hadn't even completed high school. And they produced tables of powers and trig functions and probability functions that went into the Handbook of Mathematical Functions. Did any of you, maybe your parents or grandparents, had a table of mathematical functions book? No. See, my dad gave me his. It was totally obsolete probably by the time I got it, but he was like, here, you're majoring in engineering. There you go. Anyway. In the 1940s, they also did some Army ballistics tables, right? They wanted to figure out if you shoot a ballistics, where is it going to go? So it was actually 100 or 200 women at the University of Pennsylvania were the computers, and they each had one of those desk calculating machines, like the one by Dorfeld or something like that, and they would do these computations and put them into a table. Okay. So next we're entering into the digital era, which is a big deal. So this is modern supercomputers. So computers were really developed for computing tables, which then obsoleted tables. But that was people didn't really have this idea that the computer could do this. The first digital computers had vacuum tubes and neon lamps as prototype memory. A real great one from the early 1940s was the Colossus. It was developed in 1943. They used it to crack the German codes. And they built 10 of them, and they destroyed most of them after the war. And you can see these women operating the Colossus in my picture there. Okay, the ENIAC came in 1946. It was the first really totally electronic, valve-driven, digital programmable computer. It could do 5,000 simple adds or subtracts per second. See, so really maybe this is the start of the kiloflops era. You can see it was really huge. It was Turing complete, and originally for ballistics tables, but it was actually used for the first calculations to go into the hydrogen bomb with Los Alamos. So you've seen a lot of pictures and stuff about women. I just want to take a time to shout out for all the ladies in this room. So women played a very prominent role in computing, especially early on. We heard about Ada Lovelace already. There was a woman named Emma Gifford who compiled a 500-page book called Natural Signs. And she computed sines and cosines to unprecedented precision. And I think she did it all herself. So good for her. But women were also very active in early modern computing. So they operated the ENIAC and they operated the Colossus. And of course, we've all heard of Grace Hopper, who developed the first compiler and the idea of machine-independent programming languages and a number of other things. Okay, so in this era, it was also sort of a numerical renaissance. So it was the rebirth of interest in numerical solutions of equations. So there are some really great numerical analysts of this era, probably who you haven't really heard of. So remember, we were talking about these relaxation methods, right? Where you're doing this fixed point iteration. Okay, well, in 1950, a guy named Young developed one called successive over relaxation. So it's a lot like the Gauss-Seidel method, but the difference is you have this relaxation factor, omega. Okay, and you sort of have to figure it out through some kind of arcane art, exactly what omega should be, but it's somewhere between 1 and 2 typically. So it's very similar to the Gauss-Seidel method, but it can actually be an order of magnitude faster. Okay, so birth of the modern computer, the EDSAC. This was really the first modern computer. It was constructed by Maurice Wilkes and a team at Cambridge. It was the first PhD in computer science, was to a guy named David Wheeler who invented the subroutine. Isn't that great, just to think like you could get a PhD for inventing the subroutine? So it was really huge. Of course, it was a really big thing, 4 meters by 5 meters by 2 meters. And it was the first complete, fully functional von Neumann architectured computer. So there are a lot of innovations that led to what we think of as more modern computers. So first keyboard and cathode ray tube CRT sort of TV sort of thing, 1951. Compiler, also in 1951. Transistor-based computers in 1953. Fortran, first developed in 1954. The integrated circuit in 1958. Atlas, which was a big computer, introduced many modern architectural concepts like spooling, interrupts, pipelining, etc. That was in 1962. And then the observation of Moore's law was in 1965. So a lot of things going on then that led to what we call computers. But this is really the dawn of supercomputers. So there was a machine called the Control Data CDC 6600 in 1965. It was designed by Seymour Cray. Seymour Cray is basically the father of supercomputing. So it was a mega flop. Everybody remember what mega means? Mega million, yep. Okay, 10 to the 6th. It had a plus-shaped design, and it was about the size of 4 filing cabinets, and it cost a modest fee of $8 million, which back then that was huge money. Okay, so next we come to the vector supercomputer. So Seymour Cray was at CDC for a long time, but then I don't know what happened. He had these great ideas that maybe they didn't accept there. So he formed his own company called Cray Research. And so they put out this Cray 1, okay? And it was the first to use integrated circuits. And you notice this interesting shape. It's actually sort of a C shape here. I wish we could see this picture a little better. This out here is the cooling system, and this inside here that's in a C shape, that's actually the computer. And so you could also sit on the outside here. It was kind of fake leather or something. Maybe it was real leather for the price, I don't know. But in any case, you could kind of sit on it, and he kind of advertised it like you could put it in your company headquarters in the lobby, and then people could sit on it while they're waiting for an appointment with the CEO. Seems pretty cool. Anyway, they ended up selling 85 units. I think he wanted to sell 10, sold 85. And it was a 136 megaflops machine. So we're getting pretty amazing here. So vector processing, what that means is that you're performing the same operation on an array of numbers. So like an array of multiplies or adds. These relaxation methods are perfect for vector processing because they are matrix vector operations. Gauss-Seidel and SLR, those were the best methods for this because the storage constraints and the convergence was much better. Okay, so now we're entering into the parallel era. Okay, so the thinking machine CM2 in 1987. This was really the first parallel machine, super duper parallel. It had up to 65,536 microprocessor cores in it. Okay, so this was the first time that we went from having a sort of like a vector processor to just having many, many, many processors. Okay, so that was a pretty big deal. So Moore's law has enabled performance to double every 12 to 18 months. And the way it does that, or it did that in the 1990s, was to just increase the clock rate every 12 to 18 months. Okay? So this is a picture of an Intel Paragon, and it had up to 1,024 nodes with 2 or 3 cores per node. It's pretty hot stuff then. And it was 150 teraflops. So remember what tera is? Yeah? Okay. So it was #1 on the top 500 list in 1995. The top 500 list is the list of the most powerful supercomputers in the world. Okay, so that was pretty darn parallel. But then we had to go even more parallel to get even more powerful supercomputers. So the big one on the block was the Blue Gene. IBM Blue Gene in 2004 it came out. It just had like huge numbers of very low powered 700 megahertz PowerPC processors in it. And that's how they were able to get a lot of compute power in these days, would be to just have a whole bunch of racks of this machine. Each cabinet of the machine is about the size of 3 refrigerators, and it uses about the power of 3 refrigerators. So these machines were huge behemoths that just dominated the top 500 list for many years. So now that we're doing this parallelism, this is a distributed memory parallelism. So information that we have to share between processes has to be passed as a message, which is very expensive and non-trivial. So as these machines grow in size, then the degree of parallelism just rises. So the answer was the MPI standard, which was developed in the mid-1990s for communication between distributed processes. And our relaxation methods, such as Gauss-Seidel or SOR, are no longer viable because it requires too much communication. So in fact, the Jacobi method gets back into favor because it doesn't require the same sort of communication. It has an inferior performance, but the communication cost is so much less that it's fine. It starts to be used again. But actually, stationary iterative methods kind of got replaced by what we call Krylov subspace methods, such as the conjugate gradient method or GMRes, which if you ever take numerical methods, you'll learn all about these. I'm not going to go into any detail there. So now we're getting into the present day era, the petascale era. That's 2008 through today. So the first petascale machine was called Roadrunner. It was by IBM, and it was at Los Alamos National Lab, 2008. It was 1.7 petaflops theoretical peak, but really, when you actually ran the programs, it could get 1.026 petaflops. And it was a hybrid machine, so that means it had an Opteron regular processor, and then it had a cell accelerator. And it used 2.35 megawatts of power. So these machines gained in prominence because they're actually pretty low power for what you get in the machine. So this architecture is still popular today. The #1 and #2 currently on the list are this hybrid architecture where you have a regular processor for the brains of the machine and an accelerator for the brawn to really do the floating point operations. So this requires an offloading programming model where you feed these computations to the accelerator, and it's pretty tricky. So people developed these multi-core supercomputers as well. So it's kind of two swim lanes. You've got the accelerator kind, you've got these multi-core machines. So the first petaflop multi-core machine was called Jaguar. That was at Oak Ridge National Lab in 2009. 200 cabinets, 18,688 compute nodes. Okay? On the other hand, 5 years later, the most powerful supercomputer in the southern hemisphere was called Magnus at the Posey Supercomputing Center where I used to work. 8 cabinets versus 200 cabinets. 1,536 nodes versus 18,688 nodes. And a much smaller power envelope as well, about order of magnitude smaller power envelope. Okay, so next we're going to the many-core architecture. So if multi-cores are great, how about many, right? If we can put, 24, 32, whatever, how about like 100 cores per node? That sounds fantastic, right? So each core is operates at a low frequency, but it all adds up together. The aggregate flop count is very high. So it requires a lot of preparation for this new architecture and exposing more parallelism. And in about Q3 of this year, Cori will arrive at NERSC, where I work, and it will probably be the number 2 most powerful supercomputer at that point. So that's pretty exciting. So, to review a little bit, we've got architectural innovations in the 50s and 60s. We've got the rise of the vectors. We've got the parallelism, the era of massive parallelism and clock rate scaling. We've got multi-core that comes around. We've got multi-core and accelerator-based systems. And then we've got many-core systems that are just coming today. But what about the future? This is the exascale era. 2022 is when they predict our first exascale machine will arrive. What are we going to do? Well, exascale computers have billion-way concurrency. Okay, we were talking millions concurrency before, maybe 10 million. Now we're talking billion-way concurrency. In a single node, they will have 1,000 to 10,000 parallel processors. Okay, it's pretty incredible. Without any new technologies, the memory and interconnect bandwidth won't grow at that same rate, which is unfortunate. And so we're really going to have to rethink numerical methods and how we do them. So in this future era, the exascale era, flops are effectively free. Right? They're so cheap compared to anything else that you do. Actually, even data movement is expensive. Memory is very precious. Communication is very costly. You definitely want to avoid any global syncs if you can. So what algorithms can we employ for exascale architectures? Well, yeah, how can we get from here to there, right? So here's an analogy. Let's say that we want to get to the moon, okay? We know that there's a series of trees that we can climb to get higher, to get closer to the moon. But the problem is, there's not a tree that will reach the moon. So we have to think of a different way of doing it. Okay? Another analogy. So it's kind of like a marching band. Okay? So let's say that computations are music and processors are musicians. So today's algorithms are compositions for a marching band. So your band marches in lockstep. Each member has a predefined role. Your band leader conducts, keeps everybody in time. You can use different arrangements of the same score for different sizes of marching bands, right? But a marching band is not scalable. I mean, your conductor, in the end, they can only be seen by so many musicians. You can't really lead 1 million musicians in lockstep, right? It'd be kind of difficult. So we really have to rethink our algorithms for creating music. The musical equivalent of exascale algorithms are unfamiliar to the Western ear, okay? So we're going to have to sort of create more improvisational algorithms, right? Who says we actually have to have a score, right? what if we just gave each musician certain parameters, like the key, the starting note of the scale, and just let everybody improvise? Maybe we'd have to have some sort of synchronization between neighbors so that your improvisation doesn't sound terrible with her improvisation, right? But effectively, it would be like a distributed million musician raga, right? Have I just blown everyone's minds? I think that's the direction that we're going to have to go. So, thank you very much.
You have time for questions?
Yeah.
I'm taking algorithms right now. I'm learning about fast Fourier transformation. Is there anything that seems more like promising as of that's currently in research, or if there isn't, is there something that's as impactful that happened as of recent?
Yeah. So the problem with a fast Fourier transform in terms of massive parallelism is that there's too much information that has to be shared, right? So instead of using sines and cosines to approximate a function, what we do instead is use multi-wavelets. I don't know if you've heard of that, but multi-wavelets, it's much better because they're local, like it just depends on a very local part of the function. So it approximates kind of smaller pieces of the function, if that makes sense. And it has it's called local support. So you don't have to know all of the values of the function everywhere in order to compute the multi-wavelet transformation. And it has other numerical properties that are superior to Fourier transforms as well.
Another question. You stopped at exa.
Yeah.
How about iota?
Well, yeah, that's going to be even more difficult.
Any questions? How about the size? Do we have supercomputing in the pocket?
Well, sure. Actually, you have supercomputing in your pocket right now. It's 20 or 30 years old, right? That's all.
Any questions from Daniel? Oh, there's a question.
Yeah.
Do you think we'll get to a point of where we'll look at collections of cores as sort of stochastic processes and maybe even apply more analog algorithms to analyze them? I think, for example, I think the brain works that way. I think the brain is more analog than digital.
Yeah, I think that's definitely true. And currently so I saw actually a really interesting graph the other day about intelligence, like human intelligence. And one axis is computation, and computers are completely off the charts on that compared to the human brain, right? But there's a whole bunch of other axes, like you're talking about, where computers just can't even do it.
Well, thank you again.